Hello everyone, I am Dr. Denny and I will be discussing the process of measuring and summarizing health data. So hopefully after this lecture, we will be able to meet the following objectives. So let me start off my discussion by introducing to you the different phases for data summarization. So basically, we have this what we call phases for data summarization, and my entire lecture will solely revolve on each phase. So we have phase 1, selection of variables, phase 2, selection of analytical methods, phase 3, selection of and presentation of the data you have summarized. So let's start with phase 1, selection of variables. So basically, you have learned from your previous lecture what variables are. And it is very important in data measurement, data processing, that before you can actually do data or process your data that you have collected, you need to organize your data in a manner that is understandable or easy for you to measure. So in doing that, we have this what we call, or a method of organizing your data is just what we call line listing. Okay, so shown here is a table lifted from Principles of Epidemiology in Public Health, third edition by CDC. All right, so this table would actually show you the cases of hepatitis A county in a health department from January, February 2004. So, in other words, in organizing your data or in line listing your data, you are going to list, you are going to make a list to come up with an information of the different variables that are involved in your study. You have learned that there are basically many categories or types of your variables. So this was actually our first exercise that we're in. We let you search for different PubMed articles and we let you identify what those variables are. So after you have organized, you have laid down your variables of interest, you can now select which of these variables are actually considered your primary indicators. So in selecting and defining your primary indicators, you also select and define the person, the place, the time, and the risk variables. And your primary indicators may be a health indicator, which are actually used to assess the health status of a population. So we have three health indicators in public health or in biostat. So we have this what we call morbidity indicators, mortality indicators, and population indicators. So I will be discussing each one in detail. Let me discuss first this what we call frequency of measures. If you do not understand this part of my lecture, you will not be able to easily memorize, or better, you will not be able to easily grasp the succeeding computations, because these frequency of measures are actually the basic principles or the pillars of your computations in the different health indicators. So we basically have three frequency of measures. We have this what we call ratio, and then proportion, and then rates. Okay? So ratio is a relative magnitude of two quantities or a comparison of any two values. What I want to point out here is that when we are talking about ratio, we are actually comparing two different values, such that this comparison now is expressed as the number or rate of events, items, persons in a particular group compared to the rate or number of events, items, or persons in another group. So basically, you are just comparing. two different groups. So for example, this is how you calculate ratio with different categories of the same variables. So we have this what we call National Health and Nutrition Examination Survey conducted from 1971 and 1975. So the entire study enrolled a total of 7,381 people aging 40 to 77 years of age. And then at the time of enrollment, each of these participants were classified under as diabetic or non-diabetic. Okay? And the results of the study are summarized as follows. So I want to direct your attention on the following figures here. So we have this what we call original enrollment. Okay? This refers to the number of subjects or the number of population or person enrolled at the beginning of the study. All right? And then since this study is actually a long-term study, so the study was conducted from 1971 to 1975 and follow-up were done from 1982 to 1984. And they actually found out that the participants in their study, they found out that they were dead, on follow-up. So we have here diabetic men of 189 and then dead on follow-up 100, non-diabetic man a total of 3,151 and so on. Okay? Now, you are to calculate the ratio of non-diabetic to diabetic men. Very easy, because we are given the figures above. Okay? So again, how do we calculate the ratio? We need to compare that specific number of one group to another group. In this case, we are to compare the number of non-diabetic to diabetic man. So looking at the table, we had a total of 3,151 non-diabetic men who were enrolled at the start of the study, whereas we had a total of 189 diabetic men who are enrolled in the study. Expressing this as a ratio, you have 3,151 divided by 189, we have 16.7 is to 1. Okay? So we divide the numerator with 189, we divide the denominator with 189, that's why we got 16.7 is to 1. That is the ratio. Alright? Another example of calculating ratio with different variables. So we are given with a city of 4 million people living there with 500 clinics. Okay? So we are asked to calculate now the ratio of clinics per person. Okay? So we are going to determine the number of clinics per person. Alright. So we have here the two groups that we are going to compare are the number of people living in that city and the number of clinics within that city. Okay, so the order is clinics per person. So per person, alright? So our numerator would be the total number of clinics, alright? Since we are going to calculate its ratio per person, which is now the clinics, total number of clinics represented by 500, and the total population or the number of people in that particular city is represented by 4 million. Okay? So if we actually divide it by 500, so we actually 500 by 4 million, we actually get a value of 0.00125 clinics per person. Now, this value would actually make no sense. It's because you do not have a decimal na clinic. All right? That's why we have a factor of 10n, wherein your 10n would actually depend on the number or this would actually depend on whether you were able to get a more easily understood values. So in this case, we use 10,000 because 10,000 is the nearest value wherein we could get a whole number. All right. So the ratio is 1 now. The the quotient now is multiplied with the 10n factor, which is 10,000 in this case, giving us a number of 1.25 clinics per 10,000 persons. Now, of course, we don't have 0.25 clinic. No, that's why this is better expressed as one clinic for every 8,000 persons. Okay, so next we have another example. So Delaware's infant mortality rate in 2001 was 10.7 per 1,000 live birth, and Hampshire's infant mortality rate in 2001 was 3.8 per 1,000 live birth. Now you calculate the ratio of the infant mortality rate in Delaware to that in New Hampshire. Okay, so we are comparing now infant mortality rate with of Delaware to that of New Hampshire. So the infant mortality rate of Delaware was 10.7 per 1,000 live birth. And the infant mortality rate of New Hampshire is 3.8 per 1,000 live birth, giving us a ratio of 2.8 is to 1. Okay, so thus, the Delaware's infant mortality rate was 2.8 times higher as New Hampshire infant mortality rate in 2001. Okay, so another frequency measure is this what we call proportion. So you actually discussed this with Sir Miasco, no? So I actually reviewed his video so that I will be guided which topics did he include, no? So just a review, a proportion is actually considered a part of a whole. So in other words, when we are talking about proportion, we're actually comparing a particular portion or a part of the entire whole or the entire population. So this is better expressed as the number of person or events with a particular characteristic, compare it with the total number of the person or events of which that particular characteristic is a subset. Okay? And then we multiply this with a factor, 10n. Now, proportion, as you can recall with Sir Miasco's lecture, is better expressed as a percentage. That's why a better factor, after getting the quotient or comparing the two, the subset with that of the whole group, you need to multiply it with 100, that is expressing it no as a percentage. So example, we have from the NHANES study who enrolled 189 diabetic man, 3,151 non-diabetic man, and 218 diabetic women, and 3,823 non-diabetic women. So we are to calculate the proportion of men in that study who were diabetics. Okay? And then we also need to calculate the proportion of deaths among men. So how do we do it? So in calculating the proportion of men who were diabetics, okay, so we should take note the total number of men who were diabetics in the first place. Okay, so the total number of men who were diabetics were, is represented by the value 189. If you can recall, see, 189. And this 189 is actually a portion of the total number of men participating in the study. Now, for us to get the total number of men participating or originally enrolled in the study, we need to add up the number of diabetic man with that of the non-diabetic man. So giving us a sum now of 189 plus 3,151, we get a sum now of 3,340. And how do we express a proportion? We have to compare the number of that particular subset, in this case, the number of diabetics, to the number of a particular whole. So that particular whole here is represented by the sum of the total number of men participating in the study. So in this case, we have 3,340. And then we need to multiply the quotient with 100. Why 100 again? Because proportion is better expressed as a percentage. Okay? And to express is express it as a percentage, we multiply it with 100. So 189 divided by 3,340 times 100. So we there is a parenthesis here, so we need to do the quotient first, get the quotient first, and then we multiply it with 100. We get a result of 5.66%. That is the proportion of diabetics to the total number of men. And then our second task is to calculate the proportion of deaths among men. Okay? So calculate the number of deaths among men. So going back to the table, the number of diabetic men who died in the study was represented by 100. And then the number of non-diabetic men who participated in the study and then died eventually on follow-up, we have a total of 811. Okay? Now, for us to get the total number, okay? The total number, because we need to calculate the proportion of deaths among men, So in the numerator, we need to compare the total number of death occurring in men only, no? So we have 100 in diabetic man and 811 in non-diabetic man. We get a total of 911 deaths in men, okay, which is a subset in the denominator. Now our problem would be how? How do we identify that particular whole of the population? Simple. We just need to compute or calculate the total number of deaths on follow-up. In this case, we need to include now the number of deaths in diabetic woman represented by 72 and the number of deaths in non-diabetic woman represented by 511. Okay? Now, if you add up all of these values, you get now the total whole number, the total number of people who died on follow-up. Because remember, your proportion is actually a subset of a particular whole. Okay? So in this case, the subset here is the number of deaths in men, and the whole is the entire population who died on follow-up. Okay. So in that case, we have now 911 deaths representing the total deaths in men, plus 72 in diabetic woman, and 511 in non-diabetic woman. So we have a total of 1,494 deaths. So how do we compute for the proportion? The numerator, which is 911 represented by the total number of deaths in men, divided by the total number of deaths on follow-up, which is 1,494. We multiply the quotient with a factor of 100 because, again, why? Proportion is better expressed as percentage. So we get a result of 60.98 or 61%. Now, a third frequency of measure is this what we call rate. This is a measure of frequency with which an event occurs in a defined population over a specified period of time, and this is usually useful when comparing disease frequency in different locations at different times or among different groups of persons with potentially different size populations. So I will be discussing this in detail when we talk about the different health indicators that I have mentioned. Again, what are the three health indicators that I have mentioned previously? So we have morbidity indicators, mortality indicators, and population indicators. So let's start with morbidity indicators. Okay, so morbidity is defined as any departure, subjective or objective, from a state of physiological or psychological well-being. Now, let me rephrase that in a more understandable terms. Okay, so when we talk about morbidity, you need to know first what is normal. Okay, you need to know first the state of physiological or psychological well-being. So the state of well-being or normal state will be your baseline, and any deviation from that normal state of well-being is considered now morbidity. Okay, and then in other words, no, for example, I'll give you an example. Your normal body temperature in pediatric patients, in neonates, the normal body temperature is 36.5 to 37.5 degrees centigrade. Okay. Now, any values deviating from that normal value is considered now abnormal. Okay? Why? So, in neonates, a value of more than 37.5 is considered increase. And any values considered less than 36.5 is considered decrease already or abnormal. That's why when we talk about morbidity, you need to know first the normal state of well-being, and then any deviation from that of the normal is considered now your morbidity. Okay, now this indicator answers the question, what are the health problems in the area and how many cases occur in that area? Okay, so in other words, your morbidity indicator is actually a measure of sickness, no? Measure of sickness. Now, this also measures the number of persons in a particular population who became ill or are ill at a given time. That's why I mentioned this is also termed as a measure of sickness because we count the number of people who are ill at that particular time. Okay, so this is now the problem. No, this is the difficult part now because each indicator or health indicator is actually followed by several computations. Okay, so for your morbidity indicators, we have this following measures. So for you to better understand this, I will be discussing this in detail one by one. So just for now, you need to know that under morbidity health indicator, we have this what we call a measure of incidence proportion. This is also known as a risk. And then we also have this what we call secondary attack rate, incidence rate, point prevalence, and period prevalence. No, so let's discuss this one by one. So we have this what we call incidence proportion or risk. Okay, so this refers to the proportion. Take note, class. It's proportion. So what do we mean again by proportion? We actually compare a subset, a particular portion to a particular whole. Right. So let me explain that in detail later. So proportion of an initially disease-free population that develops the disease, becomes injured or dies during a specified, usually limited period of time. Synonyms of this term are as follows. We have attack rate, risk, probability of getting the disease, and cumulative incidence. But take note, this is a proportion of an initially disease-free population that develops the disease over a period of time. So, since this is a proportion, okay, this is better expressed as the number of people who develop the disease over the entire population. So again, the number of people here would actually refer the number of people who develop the disease or injury at a specified period of time would actually refer to that particular subset of the entire population who has the infection. So the numerator is better represented with the number of new cases of disease or injury during a specified period. And since this is a proportion, we need to compare that particular portion or subset with the entire or the whole population. Okay? So we compare it with the size or the total size of the population at the start of the period. So math is better explained with examples. Okay? So example calculation here. So in a study of diabetics, 100 of the 189 diabetic men died during the 13-year follow-up period. Calculate the risk. Okay, what's the other term for risk here? It's actually your attack rate or your incidence proportion. Okay, calculate the risk of death of these men. Okay, so we need to calculate the risk of death of these men. So our numerator here is represented by the number of deaths among the diabetic men. This is actually now the subset of the entire population of diabetic men, okay? Diabetic men who died in the study. And then the denominator is represented by 189. Why 189? Because it says here, the 189 would actually refer to the total number of diabetic men enrolled in the 13 follow-up period. Okay? And since this is a proportion, it is better expressed as again, what? A percentage. Therefore, the factor that we use here is 100. Okay. So, calculating the risk now, we have the numerator represented by 100. Again, where do we get the 100? The number of deaths among diabetic men. And we divide it with 189. Where do we get the 189? This would refer to the total number of diabetic men enrolled in that study. And then we multiply the quotient with 100. We get now a value, a risk of 52.9%. Okay? So, another example here, in an outbreak of gastroenteritis, so gastroenteritis would actually mean inflammation or infection in your GI tract, okay? Outbreak of gastroenteritis among attendees of a corporate picnic. 99% ate potato salad, 30 of whom developed gastroenteritis. Calculate the risk of illness among persons who ate potato salad. Okay, so we need to compare now the number of people who develop gastroenteritis with the total number of people, no? Total number of people who ate that particular food. So our numerator is better represented with the subset, no? The number of new cases. So in this case, we had a total of 30 cases who ate the potato salad and developed gastroenteritis, divided by the total number of persons who ate the potato salad, which is represented by 99 persons. And then our factor here is 100. It's because proportion, we are talking about proportion here. Risk or incidence proportion is actually a proportion. Okay? So calculating the risk or the food specific attack rate, we get now 30 divided by 99, the quotient is multiplied by 100. We get now a product of 30.3% risk. Okay, so I hope you got that, no? Very easy. And then we have this what we call secondary attack rate. This documents the difference between community transmission of illness versus transmission of illness in a household, barracks, or other closed population. Okay. Now, what you need to remember when we talk about secondary attack rate is that secondary, no? So there are actually people who got infected first, no? Who got infected first. So we call that primary cases. And then eventually, from these primary cases, we have a number now of new people who got infected. Okay? So this basically is represented by the number of cases among contacts of primary cases. Okay? So from these primary cases who first got the infection, they had contact with close contact with another group of people or population of people, okay? And the population of that people who got close contact with primary cases are referred to as your secondary risk or secondary attack rate. So we divide, since this is a proportion, we divide it with the total number of contacts, no contacts of the primary cases. And then we multiply it with a factor of 100 because this is a proportion again, which is better expressed as a percentage. So again, math is better explained with examples. So consider an outbreak of shigellosis in which 18 persons in 18 different households all became ill. If the population of the community was 1,000, then the overall attack rate was 18 per 1,000 times 100 equals 1.8%. One incubation period later, 17 persons in the same household as the primary cases developed shigellosis. If 18 households included 86 persons, calculate the secondary attack rate. So again, we need to revolve, no, with this definition. So we need to count the number of cases who got the infection because they had close contact with the primary cases. We divide it with the total number of contacts, okay? So how do we compute with the total number of contacts? This is calculated as the number of primary cases minus the number, the total population of the household of the primary cases minus the number of primary cases. And then we multiply it with a factor of 100, okay? So let's compute. So let me explain first, no, one by one, no? How do we get the 1.8 and etc. So initially, there was an outbreak of shigellosis. No, you know what's shigellosis, okay? You usually get this by eating contaminated food or water with Shigella, okay? And the infection associated with Shigella is termed as shigellosis, okay? So usually patients with shigellosis presents with gastroenteritis, no symptoms of gastroenteritis. So we have nausea, vomiting, and diarrhea, and even some people um, presents with fever, no, associated with the gastrointestinal symptoms. So initially, there were 18 people from 18 different households got infected or got shigellosis. And the total number of population from the entire household is 1,000. So again, your primary attack rate or your risk is actually defined as the number of new cases compared to that of the entire population. So the number of new cases here, I'm talking about of primary attack rate, not yet the secondary. Okay, just to compare. So your primary attack rate here is represented by 18. Your 18 is the number of new cases who got shigellosis or infection divided by, this is a subset of a particular whole. The whole here refers to the entire population of the community, which is 1,000. So 18 who got the new cases, then the infection divided by the total number of population, the quotient is multiplied by 100. Why? It's because again, 100 represents here as a, being represented as a percentage, since your attack rate is a proportion. So we get now a risk or attack rate of 1.8%. So this is not yet your secondary attack rate. This is still your risk or your primary attack rate. So again, how do we define your secondary attack rate? So we define this as the number of contacts from the primary cases. Okay. So one incubation period later, 17 persons in the same household as these primary cases developed shigellosis. So initially we had 18. And after a period later, another 17 people got infected because they were exposed, they were living within the same household as those people who first got the infection. So this is now your secondary, no? Secondary attack rates. So we have 17 here would actually represent of the contacts from the primary cases. And then if the 18 households included 86 person, calculate the number of the secondary attack rate. Okay, so how do we compute it? So your 17 would actually refer to the number of contacts of your primary cases. So your primary cases are the 18 people who first got the infection. And since they live in the same household, another 17 people got infected. So 17 divided by the total number of the entire population. So listen here. How do we compute for the total entire population? Okay? So we subtract from the total number of the population, we subtract the number of the people who first got the infection. Okay? So we have 17 divided by 86 minus 18. So you subtract first 86 by 18 and then we multiply it with 100. So 86 minus 18 is 68. So you divide that from 17. We multiply the quotient with 100. We get now 25% secondary attack rate. So very easy, no? So another indicator of morbidity is this what we call incidence rate or person time rate. This measure of incidence incorporates time directly into the denominator. So this is calculated from a long-term cohort follow-up study wherein enrollees are followed over time and the occurrence of new cases of disease is documented. So this refers to the ratio of the number of cases to the total time the population is at risk of the disease. So we basically have two ways in computing or calculating for your incidence rate, no? Your incidence rate is also known as person time rate or in abbreviation IR. All right. So how do we compute this? So in the numerator, this is represented with the number of new cases during that specified time. Because again, incidence rate is an expression of person time rate. Okay? Number of people or person who got the infection at that particular period of time. That's why it's also called as person time rate. Alright. So the number of cases during which a specified time divided by the total number of population in that particular area during that time. Okay, and since um, IR here represents incidence rate, so we multiply it with a factor. Okay, so this is also expressed as the number of new cases of disease or injury during that specified period and the time each person was observed totaled for all people. So in other words, no, the total population during that time. So example, in 2003, 44,232 new cases of AIDS were reported in the United States. The estimated mid-year population of US in 2003 was approximately 290,809,777. Calculate the incidence rate of AIDS in 2003 at that particular time. Okay? So again, how do we compute for your incidence rate? We need to compare the number of cases or new cases no, who got the infection, who got ill, with that of the total number of people or the entire population at that particular or specified time. Okay. So in this case, the new cases here would refer to the number of people who has AIDS. No? So we have 44,232 new cases of AIDS. And then the denominator, take note ha, new cases. And we need to compare that with the total number of population, which in this case is 290,809,777. And then our factor here is 100,000. So our factor would actually matter, no? Depending on which, again, I mentioned in the previous slides, depending on which values would give us a reasonable count, no? Or more significant values. Okay? So incidence rate, so we compare 44,232 with that of the entire population now. And the quotient is multiplied with your factor, which is 100,000. So we get now a total number of 15.21 new cases of AIDS per 100,000 population, or in other words, 15 cases of AIDS per 100,000 population at that particular time. Another example. So the diabetes follow-up study included 218 diabetic women and 3,823 non-diabetic women. By the end of the study, 72 of the diabetic women and 511 of the non-diabetic women had died. The diabetic women were observed for a total of 1,862 person years. The non-diabetic women were observed for a total of 36,653 person years. Calculate the incidence rates of death for the diabetic and non-diabetic woman. So do not confuse yourself here because person years is actually an epidemiologic term, no? Or in simpler term, this refers to the person per year, person on that year who got that infection, okay? Person years, person per year, okay? So we need to calculate the incidence rate for both diabetic and non-diabetic woman. Incidence rate of death, okay? So for diabetic woman, we had a total of again 72 diabetic women who died. All right. So 72 here would represent the number of deaths occurring in diabetic woman in that particular period of time. And then we divide it with the total number of diabetics enrolled in that study, which in this case is 1,862. So we get now a 0.0 0.0386 deaths per person year. So again, the decimal here would not is actually not a reasonable um, number because we could not count the number of people who died with decimals. No, it has to be whole numbers. So the factor that we have used here is 1,000. Okay, to get now 38.6 deaths per 1,000 person years. So again, class, do not confuse yourself, sir or doc. Um, we do not know which factor to use, no? How about in the examination, doc? We do not know if the factor that you are thinking, if you are thinking the same factor, no, we might use 1,000 and then you might use 100,000 or you might just use 100. Okay? Do not worry, class, because this will be specified in the question. For example, calculate the incidence rates of death for diabetic and non-diabetic woman per 1,000 person year. So I will really specify that, no, for you to easily get the answer. Okay, so that will be specified, or if not specified in the question, it will be specified in the choices. So A, 36.6 deaths per 1,000 person years. B, 40 deaths per 1,000 person years, etc. So it will be specified. Do not worry. Okay, that's not for you to think about. And then our second task is to calculate for the non-diabetic woman incidence rate. So the total number of non-diabetic women who died is represented by 511. Okay? 511. And we compare it with the total number of non-diabetic person who participated in the study represented by 36,653. So we calculate that, we get the quotient, we get a value of 0.0139 deaths per person. Okay, so again, this is not a reasonable value. So we multiply it with 1,000 as a factor, we get now 13.9 deaths per 1,000 person years. So again, class, while you are listening to this lecture, it would be better if you calculate with me, because the more senses you use when you study, the more you retain those information. No, do not just watch the lecture and do nothing there. Okay, so you calculate with me so that it will be easy for you to remember or retain these information, especially know that my examination will be purely calculation. So another morbidity indicator is this what we call prevalence, also known as prevalence rate. So again, this is a proportion of persons in a population who have that particular disease or attribute at a specified point in time or over a specified period of time. This differs from incidence in that the prevalence includes all cases, both new and pre-existing. Okay. Whereas your incidence is limited only to the number of new cases. Take note, when computing for prevalence rate, we need to include the number of people who initially got the disease and the number of people who just got infected. Okay, in other words, we need to include the old plus the new cases for us to get the prevalence rate, comparing it with the total number of population. So example. So before I proceed to example, we need to define these terms. So under prevalence rate, we have this what we call point prevalence and period prevalence. So point prevalence refers to the prevalence measured at a particular point in time, and then period prevalence measured over an interval of time. Okay, so when we talk about period, we're actually talking about a range, no particular interval of time. Whereas if we talk about point prevalence, we're talking about a point, a particular point in time. So this is how we calculate your prevalence, okay? So the number of new and pre-existing or old cases during that particular period of time divided by the total number of population during that same time period, multiply it with a factor, okay? And then another method for calculating prevalence of an attribute, the persons having that particular attribute or condition during that specific period of time, we compare it with the total number of population during the same period of time, we multiply it with a factor. Okay? So the value of 10 is usually, the factor is usually 1 or 100 for common attributes. But the value might be 1,000, 100,000, or even 1 million for rare attributes for most diseases. Okay. So that is to better express or to better get a significant no reasonable na values. So example, in a survey of 1,150 women who gave birth in Maine in 2000, a total of 468 reported taking multivitamin at least 4 times a week during the month before becoming pregnant. Calculate the prevalence of frequent multivitamin use in this group. Okay. So, we need to first, again, we need to go back on the definition of your prevalence. Okay. So, prevalence or prevalence rate refers to the number of old and new cases, no, compared to that of the total population. Okay. So, the total number we are given here with the total na, no? The total number now of people taking the multivitamins is 468. Okay? And then we compare it with the total number of people who are pregnant, no? Or the total pregnant population at that time, the survey was done was 1,150. So again, we need to compute for the number of people, the prevalence, the rate of people who are actually using the multivitamins versus the number of people who do not take the vitamins, no? So we include that also in the total. Okay. So how do we compute it? 468 represents the number of incidents, the total number of incidents or the users in this case of the multivitamins divided by the total number of population, and then we multiply it usually because this is a proportion, a factor of 100. But again, take note, the factor could be 1,000, 100,000, 10,000, or even 1 million. Depends no if we are talking about rare conditions. Okay. So we get now a quotient of 0.407. We multiply it with 100, and so we get a prevalence rate of 40.7%. Okay, so very easy. Now we're done with the different morbidity indicators. Let's discuss the different mortality indicators. Okay, so your mortality rate is a measure of the frequency of occurrence of death in a defined population during a specified interval. Okay, so this is when we are talking about mortality, we're actually talking about the number of death which has occurred, no? The number of death. And then we compare that number of death with the total number of population among which the death has occurred. So the number of death versus or compared to that total number of population from which this death has occurred. And then we multiply it with a factor. So for example, here. So we have different measures of mortality. Okay, mortality indicators. So we will discuss this one by one. So this table here summarizes the entire discussion on mortality indicators. So we have this what we call crude death rate, cause-specific death rate, proportionate mortality, death to case ratio, neonatal mortality rate, postnatal mortality rate, infant mortality rate, and maternal mortality rate. So let's discuss this one by one. So let's start with crude mortality rate, also known as crude death rate. Okay? Mortality rate is also known as death rate. Take note, ha? Mortality rate is also known as death rate. So this refers to the mortality rate from all causes of death for a population. Why is this term, or why is this called crude? It's because we do not distinguish, we do not discriminate what is a particular cause of that death. We just count crudely, roughly count the total number of deaths compared to the total number of population. So your crude death rate, also known or abbreviated as CDR, is calculated as the total number of deaths. No, we do not specify what has caused the death or what particular disease causing the death, divided by the mid-year or the total number of population in that same year which the death has occurred, and then we multiply it with a factor. Okay. So for example, a total of 396,331 deaths were registered in the Philippines when it had a mid-year population of 49,543,000 in 2003. Compute for the crude death rate. Okay? So again, how do we compute it? We compare the total number of deaths occurring in that particular period of time. So the time is 2003. Compare it with the total number of population in that particular period of time. Okay? So the total number of death occurring, total number of death, no? You do not specify the cause of death. You do not break this down into what particular disease has caused the death. So we have 396, 331, the total number of death. Compare it with the total number population at that period of time in 2003, and then we multiply it with a factor of 1,000. So we get 8 deaths for every 1,000 population. So how do we interpret it? So there are a total 8, so 8 Filipino die for every 1,000 population in 2003. Okay? So another example, in the United States in 2003, a total of 2,419,921 deaths occurred. The estimated population was 290,809,777. That is in 2003. Compute for the crude death rate per 100,000 population. So the reason why I showed you this example is that it is not always that we use 1,000 na factor. Okay? If not specified, we use 1,000. But since I mentioned no a while ago that if I specify the factor to be used, then you need to use that factor. Okay? So per 100,000 population. So the crude mortality rate in 2003 was the total number of death, which is 2 million here, divided by the total number of population in that particular year, which is 290. We multiply the quotient with the factor, which is 100,000, or we get now 832.1 deaths per 100,000 population. No, very easy. Next, we have this what we call age-specific mortality rate or age-specific death rate or ASDR. So why do we call it as age-specific? Because this is limited to a particular age group. In other words, we are actually talking of a certain cause of death, of a certain death in that particular age group only. Okay? So, in other words, the numerator is expressed as the deaths in that age group compare it with the total number of person in that age group, population, total number population. Okay, and this is computed as follows. The total number of death in that specific age group, we compare it with the total number of population in that same age group on which that death has occurred. And then we multiply this with a factor. Okay, so example, given the following data, the number of people who died in the age group 1 to 4 years of age is 36,250. And the total number of population in that age group in that same year is 5,629,300. Compute for the age-specific death rate or age-specific mortality rate. So again, what do we compare? The total number of deaths in that particular age group in that same year, in that particular year, we compare it to the total number of population, okay, from which the death has occurred in that particular age group. Okay, so the total number of deaths is represented by 36,250 in that age group. The age group is 1 to 4 years of age. And then we compare it with the total population of the 1 to 4 years of age, which is 5 million. We multiply it with a factor of 1,000. We get now an age-specific death rate or mortality rate of 6.44 or 6 deaths per 1,000 population. Another mortality indicator is this what we call cause-specific mortality rate or cause-specific death rate. So this is mortality rate from a specified cause for a population, and this is now know what I mean, because in crude death rate we just compute for the total number of death without specifying or without discrimination or discriminating that particular cause of the death. No, we just count the total number of the death, and that will give you your crude death rate. But your cause-specific death rate or cause-specific mortality rate, you need to really identify the different or specific causes of the death. So you do not you do not count the total, no? From that total, you need to specify the cause of each death. Okay. So this is expressed as the number of deaths attributed to a specific cause, and the denominator remains the size of the population at that midpoint of the time. So to explain this in simpler manner and simpler way, so for example, in this month, we had a total of 1,000 deaths in the population for this month, huh? For this month. Now, of the 1,000 deaths, 25 died from heart attack or acute myocardial infarction. So, if we are talking about crude rate, you will use 1,000 as your numerator. But if we are talking about cause-specific death rate, so you compute for the number of people who died from that particular disease. So in this case, acute myocardial infarction. So we have 25. Okay. So you see the difference, no? It would really matter. So the factors affecting this health indicator are as follows. We have completeness of registration of deaths, composition of the population, and disease ascertainment level in the community. So example here. So we have the total number of deaths occurring due to pneumonia in 2001 equals to 43,349. So this is the death from pneumonia, due to pneumonia. And the total number of population in that same year is 42,517,300. Compute for the cause-specific death rate or mortality rate. So again, we need to compare the number of people who died from that particular disease specific disease with that of the total population in the same period of time. Okay, so in this case, we have 43,000 total of your pneumonia cases. Pneumonia death, no, deaths caused by your pneumonia. And then compare it with the total number of population, which is 42 million. So the quotient is multiplied by, again, Doc, why not 1,000? So again, I mentioned it would actually vary, no, depending on which values will give you a more reasonable, significant figures. So we use 10,000 here, but do not worry because I will be specifying that during the examination. So this would give us now 10.2 or 10 people who died for every 10,000 population from pneumonia. No? 10 people died from pneumonia in every 10,000 population in 2001. Okay, so another mortality indicator is this what we call case fatality rate. So this measures the killing power of the disease or injury, and a high CFR or case fatality rate means that the disease is more fatal. So this is usually useful in acute infectious diseases given that all new cases are reported and most deaths occurred in relatively short time after diagnosis. So again, this is a measure useful for acute cases. Okay. So how do we compute this? All right. So your CFR is dependent on the nature of the disease, the diagnostic ascertainment, and the level of reporting in the population, and this is expressed as a percentage. No, in other words, this is a proportion. So your CFR is computed as the total number of deaths for a particular cause at that specified time over the total cases of the same cause follow up at a specified time. So let me explain that further no, by this example. So we have 500 reported cases of pneumonia in Cebu in 6 months period, and 436 of these 500 cases died. So you got now the point. We are actually computing the number of deaths from a particular cause, from a particular disease. So what we need to determine is the total number of people who got that disease. So in this case, the total number of people with pneumonia. And from there, we need to determine the total number of people who died from that particular cases with pneumonia. Okay, so in this case, we have the total number of people who died from pneumonia is 436. We compare it with the total number of cases with pneumonia, which is 500, and then we multiply it with 100. So you have now a case fatality rate of 87% of all pneumonia cases. In other words, your case fatality rate would actually mean the risk of dying after getting that particular disease. Okay? So 87% of all pneumonia cases in a 6-month period in Cebu City died. So another mortality indicator is this what we call infant mortality rate. So this is most commonly used measure for comparing health status among nations. And this is widely used measure of health status because this usually reflects the health of the mother and the infant during pregnancy and the year thereafter. Okay, and a high infant mortality rate would actually mean low levels of health standards due to poor maternal and child health care, nutritional problems, poor environmental sanitation, poor or deficient health service delivery, all of which will actually contribute to death of the infant. Okay, so how do we compute your infant mortality rate? So again, we need to define first what is an infant. Okay, so your infants are actually that part of the population who are under 1 year of age. So under 12 months. So Under 12 months, it's still considered an infant, but beyond 12 months, it's not an infant anymore. So your IMR is computed as the number of deaths of infants under 1 year of age compared it with the total number of live births registered of the same population on the same period of time. And then we multiply it with a factor. Okay. So example. So this can be divided no into neonatal mortality rate and postnatal mortality rate. Okay? So we have neonatal mortality rate is computed as the number of infants under 28 days of age. Okay? Because if you are a neonate, no, neonate the age group, no, or the age of neonates are considered to be less than 28. Okay. And the number of deaths occurring in neonates is usually due to prenatal or genetic factors. Okay. So mga inborn nga diseases. Right. So how do we compute it? So the number of infants under 28 days of age, okay, the infant is actually represented by those number of population under 28 days no from birth, and then we compare it with the total number of live births, and then we multiply it with 1,000, which is your factor now for this NMR computation. And then we have this what we call fetal death rate. Okay? So your fetal death rate would actually refer to the number of death, no, or the total number of death occurring at 20 weeks gestation, compare it with the total live birth of the same year. So class, you might be bombarded no with so many formulas here. But for infant mortality rate, what I want you to remember are the specific age no on which we consider this as that age no or terms. So for example, infant under 1 year, neonates under 28 years, 28 days, okay? And then fetal or fetal death rate at least 20 weeks of gestation. So that is what you need to remember. You compare it with the total, again, total live birth of the same year, and we multiply it with a factor of 1,000. Okay? So for example, the total death of babies who are in the 20th week of gestation is 245. And the total number of live birth, okay, on that same year is 35,960. So we calculate for the fetal death rate or fetal mortality rate. So we compare the of number of babies who died who are in their 20th week of gestation or fetal no. So 245 divided by the total number of people in that same population, no? Total number of people who were born alive in that same year, which is 35,160, and then we multiply it with a factor, we get now 6.8 or 7 per 1,000 live birth. So how do we interpret that? There were 7 fetal deaths for every 1,000 live birth in the Philippines. Okay, very easy. No, you just need to familiarize the formula. Next, we have this what we call maternal mortality rate. So infant mortality rate, fetal mortality rate or fetal death rate, and then neonatal death rate actually talks about the death of the baby. Now, if we talk about maternal mortality rate, we're actually talking about the number of deaths occurring no, in the mothers, okay? So this measures the risk of dying from causes associated with pregnancy, childbirth, and puerperium. Okay, puerperium is actually the period of time after childbirth or the postnatal period. So this is affected by maternal health practices, diagnostic ascertainment of maternal condition, and completeness of registration of birth. All right. So the numerator is actually the total number of deaths during that specific period, okay? Or within 42 days of termination of the pregnancy. Whereas the denominator is the number of pregnancies occurring Okay? The total number of pregnancies occurring on that particular same year leading to live birth. Okay? So, MMR is best expressed as, or your maternal mortality rate is best expressed as the total number of maternal death in that particular period of time, comparing it with the total number of live birth in that same period of time. We multiply it with a factor of 1,000. For example, maternal deaths for the Philippines totaled 1,698 in 2000. Using the total number of live births for that year, which is 1,766,440, compute for the MMR. Okay, so how do we compute it again? We count for the total number of maternal death in that particular period of time. In this case, no, in year 2000. So the number of moms who died during that time, no, due to pregnancy was 1,698. And then we compare it with the total number of population on total number of mothers who gave who were actually who gave live birth, no, who are alive at that time, is 1,766,440. So we multiply it with a factor, we get now 0.96 or 1 per 1,000 population, or 10 per 10,000 population. Okay? So how do we interpret that? There was one maternal death for every 1,000 live births in the Philippines in 2000, in the year 2000. So the last health indicator is this, what we call population indicators. Okay, your population indicators. So your population indicators are also known as natality or birth measures. So these are population-based measures of birth, and this is used primarily by persons working in the field of maternal and child health, and this basically also includes other population dynamics that can affect the age sex structure of the population. So these are the different measures, no, that I will be discussing. So we have crude birth rate, crude fertility rate, crude rate of natural increase, and low birth weight ratio. Okay, so first we have this, what we call crude birth rate. So this is affected by fertility or marriage practices, sex and age composition, and birth registration practice. So why do we again call this crude? Because we do not specify, no, we do not specify that particular birth, no, if that is a successful total live birth or not. But we term it as crude because we just count for the total population of live birth. Okay? So live birth, all right. So how do we compute it? So we count the number of the total population live birth, okay? So who are or who are people who are capable of giving birth at that particular time. We compare it with the total population for that year, and then we multiply it with a factor of 1,000. And so, for example, we have Bohol registered a total of 22,609 live births in 1985. The mid-year population for that year was 571,800. Determine the crude birth rate. So again, how do we compute for the crude birth rate? We determine the total number of live births in that particular period of time. In this case, the period of time is 1985. And the total number of live births in 1985 is represented by 22,609 live births. We compare it with the total number of population at the same time, in that same time, which is represented by 571,800. We get the quotient and we multiply it with the factor of 1,000. We get now 39.54 or 40 live births. So there were, interpretation, there were 40 live births in every 1,000 population in Bohol in 1985. So you might ask, no, for students who overthink, Doc, how do we know, Doc, nga we are to use the decimal form, or how many decimal places that we should use, or should we use whole number, when do we round off, no? So that we will have the same answer. Okay, so it will actually depend on the choices. If the choices are whole numbers, then you need to round off, or if the choices are in decimals, then you don't need to round off anything. Okay, so depending on the decimal places. So if you got 39.544444, all right, for example, so I only wrote here two decimal places, so that's that you need to round it off to at least two decimal places. Okay, so it depends on the choices class. And then we have this what we call general fertility rate. So this is more refined because this makes use of the number of women of childbearing age. Okay, more refined because it's actually the woman who gave birth who are capable of bearing a child. So this refers to the reproductive age group, and which is in the Philippines is defined as 15 years of age to 44 years of age. Actually, for me class, no, I would like to contest with this definition nga 15 to 44, because some girls or some women actually start their menstruation or have their menarche at age of 12, and as soon as you start your menstruation, you are actually capable of giving birth already. Okay, so 15 is actually um for me, ha, this is contestable, no, especially if you study OB, no. And then 44 also because there are actually people who do not have their menopause at 45, 46, 47. It would actually vary, but for examination purposes, you need to follow the 15 to 44, huh? 15 to 44. Some countries, no, it depends, no, 15 to 49 years po nila, ha. But for my exam, you follow the 15 to 44 na childbearing age. Okay? So, your general fertility rate is computed as the total live birth in that particular year or period of time. We compare it with the population of women who are capable of giving birth, no? Who are at the age of 15 to 44. Example, so the mid-year population of women aged 15 to 44 is 9,227,500 in Region 5 in 2003. The total live birth for that year is 1,227,600. What is the GFR? Okay, so how do we compute it? So again, we express the total number of live birth for that particular period of time, in which in this case the time is 2003. And the total number of live birth in 2003 in Region 5 is 1.2 million. We compare that with the total number of the population of women who are capable of giving birth, or in other words, women of childbearing age at 15 to 44 years of age. It gives us now, it is represented by 9.2 million. And then we get the quotient, we multiply it with the factor of 1,000, we get now 133.03 or 133 live birth. No, of course, it would be reasonable to express the answer in whole number because you do not give birth, no, to 0.03 nga kuan person. Okay? So there were 133 live births in every 1,000 population of women of childbearing age in Region 5 in 2003. And then we have age-specific fertility rate. So this is an accurate study of fertility rate in a particular specific age group. And this permits in-depth study of the impact of birth control measures of fertility, the differences in fertility at specific ages throughout the reproductive period. So this is how you calculate for the age-specific fertility rate. So BI divided by PI times K here, which is the constant. So your BI would refer to the total number of live birth registered during that particular year, no? In that age, specific age interval. divided by the total number of female population in that same age group in your numerator. We multiply it with your constant taken as 1,000. Example, if there were 705 births registered at 425,000 women of 18 years of age, what is the age-specific fertility rate for 18 years old woman? So again, how do we compute for ASFR? We count for the total number of women who are capable of giving birth, no? Live birth in that particular age period. So we have 705. And then we compare it with the total number of women at that particular age, which is 425,000. We multiply the quotient with your factor 1,000. We get now 1.66 or a whole number of 2 registered births. So how do we interpret? There were 2 registered births in every 1,000 population of women age 18 years of age. So now we're done with the computation part of my discussion. Okay? So phase 2 would actually mean selection of analytical methods. No? Now you learned all, no, all the different computations. Now you just need to select which of these computations or analytical methods would you use, would actually be of use in your study. So this involves decisions about how the indicators will be selected. Okay? So you just choose which indicator to use for your particular, so case-to-case basis. Okay? So some indicators might be presented as counts and some as rates. So we have mortality rates, fertility rates, and morbidity rates. And some might be presented as just an average. And some might be presented only in their original form, while some might be presented into categories, ranks, or scores. And when we select for analytical method, we actually group the indicator values into discrete categories, okay, alleviating the data burden. And we also do ranking and scoring methods like categorization, increasing the interpretability of data. So what I want to point out here is that when you select for analytical method, you just actually choose which one is applicable to your study. Okay? And then your phase 3 would actually involve selection and presentation. So after you have computed, after you have selected your variable, and then you selected which analytical method you are going to use, then you are now ready to present your data. And I will teach you now how to present your data. So you need to listen because you will really use this in research. This is how you will present your data in research. Okay? Not just in research, but mostly mga epidemiologic mga data or public health data. So this basically involves designing a report that effectively communicates the result of the analysis. Okay? So I want to point out, let me break down the terms here. So designing a report. Okay. So this would actually mean that you present, you present your data that you have gathered, the data, the different computations that you have made. You present now your result in a manner in which these data now would be easy to chew, would be easy to understand by the people who are actually using the data. And we actually have so many ways on how to present your data. We may make use of narrative tables, charts, graphs, or maps, depending on the type of data being presented. And this is also used, we present this data to facilitate interpretability. So data may be presented in a narrative or textual method. Data may also be presented in tabular or frequency method, or data may also be presented in graphical presentation. Okay? So I will be discussing this one by one. So let's start with narrative presentation of data. Okay. So your narrative or textual method of presenting data involves simple narration or just basically storytelling. Okay? And this is basically appropriate for small data or data with limited summaries. And this the drawbacks no for narrative data is that this can be confusing, and there are actually people who loves to see images no, so this might be boring for them no, if they're actually reading really long passage. And this is not actually applicable for very large data set. Okay, and it's difficult to see comparison and interrelationship among data. Okay, so for example, so this is actually a narrative form of data, no, which I lifted from my published research, no. So the research that I have published just this year was all about Filipino nurses in Cebu City, no. We actually measured their willingness to care to patients with COVID-19. So this research which I did with my colleagues was published in an international journal from Journal of Environmental Science and Public Health in 2002. Okay? So in narrative data, you just actually are telling stories, what your data is all about, what are the results are all about. So this might look boring, no, but for us researchers, this would actually mean a lot because this will give us a lot of information. So for example, um, most of these nurses, the nurses who participated in the study were females, 70.80%, age 20 to 25 years old, 54.01%, single, 89.78%, and mostly are college degree holders, 90.51%. And in terms of length of working experience, most of them are having no have served the hospital for 1 to 3 years, no, while a small proportion had served for at least a decade, represented by 64.96% and 2.92% respectively. And the results of this study revealed that common sources of information to COVID-19 include the internet, no? 99.27%, social media, government health website, and television news. So, um, as students, you will not really get to appreciate this type of presentation of data. But if you are a researcher, you would actually pick out so many information from this data alone, no? Okay. So another way of presenting your data is via tabular or frequency distribution. Now, this is a more easy way, a more solid way of presenting large data sets of detailed information. And this is actually a comprehensive, more orderly, and a way of comparing trends or figures. So it complements with textual presentation which can present highlights. So usually you present a table and then below you do a narrative or textual presentation. So your narrative or textual presentation would explain what's in the table. So previously, this narrative way of presenting the data is actually preceded by a table, no? But I did not include the table. All right? So disadvantage, some researchers or people do not know how to correctly interpret the tables. For example, so I will give you example later, but let me just run through no, on how you should know that you are actually creating a good table. So these are the guidelines no on to follow for doing or creating a good na table or figure. So you need to use clear and concise title, okay? Describing the person, the place, and the time. And then you label each row and each column. There must be a label of each row and column, including the units of measurement. And then show the total for each row and column where appropriate and show percentage to give the total. And then explain codes, abbreviations, or symbols, and note for the source of data in the footnotes. Okay, so I'll explain that one by one. So here, how do we make tables? So again, I mentioned it must be clear, it must be concise. Okay, so every table must be self-explanatory, meaning you don't need words, you don't need to explain that table such that the reader now, when they look at the table, they must be able to understand your table. That is the only way that you could tell that your table that or figure that you have created is actually self-explanatory, clear and concise. Now, clear when the textual discussion jives with the table, direct when necessary details are included, no only necessary details, and simple if there are no unnecessary data or markings. So, for example, so your table must be self-explanatory. So let's identify no, if this table is self-explanatory. So the table here is titled Reported Cases of Primary and Secondary Syphilis by Age in the United States in 2000. Now we have columns here. No, the columns are represented by, the first column are represented by the age group in years, whereas the second column is represented by the number of cases of primary and secondary syphilis per age group. And then below, you see the footnotes, no, you see the source wherein this table was lifted. So is this self-explanatory? Can you readily identify the number of cases per age group? Yes. Okay, are the data clear and concise? Yes, because each age group is actually um, corresponds to a particular case, no, for that age group, and the columns are actually properly labeled. Okay, so correct, no. So this table is actually self-explanatory. So this is a good table. So the title should be clear and descriptive. Clear and descriptive. It should give information about what, where, how, and when the data were taken. So, obscure data would be demographic data, meaning kulang. No, what about the demographic data? Are you putting in that table? Must be complete. So, a better title would be demographic data of applicants for college. Too verbose or too lengthy or too wordy would be demographic data of high school undergrad applying for admission to the university. Okay, so for example, we go back to that same table. The title is Reported Cases of Primary and Secondary Syphilis by Age in the United States in 2000. So we need to answer the questions who. So we're actually who. Okay, so we're talking about people with primary, secondary syphilis. Okay, what? The number of cases for each age group, where the study was conducted, or this data is true in the United States, and when this study was conducted last 2000. Okay, so very clear, very concise, and descriptive of the entire table. Alright, and then each characteristic may be summarized and compared separately by using percentage or any other appropriate procedure. If there are more than one information available for one subject, several columns may be constructed in one table and each column should be properly labeled. Let me explain that by using this table. Okay, so we have the title here correctly identified, and we also have the number of the table. Take note, the table must have a number. So table 1, table 2. So this would mean that this is the fourth table, no? The first table among the fourth tables. Okay? Reported cases of primary secondary syphilis by age in the United States in the year 2000. So, the table may have several columns. You may create several columns. And each column must be labeled correctly, labeled clearly. So we have the first column labeled age group, second column labeled number, third column labeled percent, and fourth column labeled as cumulative percentage. Now, for you to get the total number of each cases for the entire age group, you add it up, no? So you have another or separate row for total. And it would be better to express, no, for this data to be actually more significant or more usable. Okay? So we express this as percent. So if you express this as percent, there must be percentage, total number of percent. And then the cumulative percent would be on another or separate column. Now, if you need to explain something, it must be explained in footnotes. Okay? In this case, percentage in the footnotes, it says here percentages do not add up to 100,000% due to rounding error. And and also in the footnotes, you get to see the total, no, or the source, the data source wherein you have gathered that particular table, wherein you have lifted that table. Okay, so footnotes are necessary. And then usually this is placed at the bottom of the table. Okay, so footnotes are placed at the bottom of the table. Okay, so table number must be seen also, and these are usually used Arabic numeral, no, but actually could be Roman numeral, no, or Arabic, no. It actually depends, no. And then you also place the table number on the first line of the title on the single line. So the number, so you see, it's placed before the title, and then the title must be complete and concise, and you capitalize all the first words except for prepositions. Okay, so column heading should be centered on the columns where they belong, and row headings or stabs indicates the basis of classifications of the rows or horizontal series of the figures. Okay, so for example, so we have table 1 here. This is actually the correct way of writing, and then followed by the title, of which you need to capitalize each word except for the preposition. And then your columns are actually labeled, no, has subheads here, and then your rows actually also has labels. Okay, and on the footnotes, these are actually placed at the bottom. Right, so this is a good table. Now, the body should contain the figures, no, within the cells. Usually this is aligned, no, by the decimal points, and consistency in the number of decimal points should be followed. An empty cell should be indicated with either a zero or a hyphen. It should never be left blank. Okay, so going back here, no, it should never be left blank, and or if zero, could be, you can write zero or hyphen. All right, so footnotes are found usually at the bottom, and the sources of data also follows the footnotes. Okay, so for example here, so footnotes shown below. All right, so try this. So you tell me if this is, let's examine these tables, no? So try this. So a table, we have the label here, the name of the table and the title. Okay, all capitalized first letters except for the prepositions, and then each column is properly labeled. Okay, and the rows also. And then we also have a footnote, no? Footnote telling us here the source of the table. So this is actually a good, very good table. Next, we have a table, another table. Okay, so let's examine the okay, so the table is labeled table 7. No, so correct. So it has a label, and but the title here is actually wrongly placed. No, why? It's because it has to be, the first letters must be capitalized except for the prepositions. I have here kay small letters, no? But the other parts of the table, the body, the labels are actually there, and the footnotes are placed at the bottom, no? And also there is no source where the table was lifted. So this is actually not a good table. Not a good table because of the title and then the citation, ha? All right. Okay, so next slide. Another table here, table 1, no, correct. There is the number of the table. However, again, the title is not written in a way wherein the first letter must be capitalized except for prepositions. But, of course, the columns are correctly written, no? And then there are actually numbers per cell in the figure. And then we also have correctly, no, labeled na rows. But there's actually no citation, no, where the table was actually lifted. Okay, so next we have here, this is actually a poorly made na table. Why? There's actually no name, no what table number. Basin gid no siya gyud ang usa no. Basin mo ra gyud ang table, so no need for number. Okay, anyway, let's just say no, na this is actually a part of so many tables. So you need to write the number if this is table 1, 2, or 3, etc. And followed by the title, which is correctly written. No? So we can we can answer the questions. What, no? The confirmed COVID-19 cases, where in Cebu City and when. And then, and the table columns are actually labeled correctly, no? So the numbers are placed in the center, centered align, and we also have percentages, but there's no total. Okay? And in the footnotes also, there's no citation on where you got the table. Very important as citation class. Otherwise, you will be charged with plagiarism, huh? Especially when you do research. Okay. And another table. So we know the source is from Rappler because of the symbol here. But this is a poorly made table. Why? No table number, and the title is written all caps lock. Okay? So, and Cebu City positivity rate. So the title is actually not concise. It does not tell you what is that positivity rate. What is it? What is this all about? Are these COVID cases? Are these HIV cases? Or are these people who are positive with positive outlook in life? Okay. So and then we don't have total, no, total number of people tested, and we don't have also citations. So from Rappler, so a poorly made table. Another is we have table 3.9 marks of students. So this is actually also not a this is actually wrong way of writing the table number, because it must precede the title, no, must be placed here. However, the columns are actually written well, and the numbers in each cell are actually centered aligned, and you actually have a total here. Okay, however, no citations on where the table was lifted. All right. So another way of presenting your data is through graphical presentation of your data, no, through graphs, no. So this is actually a effective, no, effective way, in such that this is simpler to understand because of its way it is presented. And this may actually uh, be used, no, in when doing or when collating or presenting data with larger subsets or larger complexes masses of data. And you may actually tailor this graphical presentation of data in a way wherein it will be appealing to the audience, no? You can add colors, you can add figures, and so on. However, some, not all, actually knows how to interpret this type of data. Okay? So let's start by discussing on how to make graph. So the graph should be clear and concise, the title, and it should indicate the following. What is being represented, the place where the data relates to, and in the case of secondary data, the source of the original data should be written in the footnotes. And the scales also should be properly labeled, and legends should be used, okay? And there must be grids or guides, rulings. This will actually serve, no, for us to easy to interpolate, no, figures or data in that particular graph. And then it must be neat and business-like quality. So neat looking. So there must be, it is actually represented as in the horizontal, the label for the horizontal are usually represented by the frequencies, and vertically usually the frequencies. Again, classification is usually represented in the horizontal scale, whereas the frequencies are represented in the vertical scale. And in the vertical scale, you always start your measurement with 0, and you may opt to use color for emphasis, no? So, example of your data, no? We have line graphs. So this is actually used for trends or data showing patterns, or basically when you are dealing with time data. Okay, so used to show long series of data to compare several series, and this is the method of choice for plotting rates over time. Okay, so the title of the graph must be descriptive and clearly stated, and the x and the y axis should be scaled and labeled, and the sources and footnotes should be provided when necessary. Okay, so the 0 point should be equal spaces with the scaled units, and the graph should be not be loaded with too many curves. And the axis may be shown, we show a broken line to indicate that some points in the scale are unnecessary. So example, so we have the label is usually found at the bottom. Okay, so the vertical axis and the horizontal axis are properly labeled, and the scale in the vertical axis usually starts with 0, and each scale units are actually represented with equal distances. Okay, and each point of the graph um, would actually mean a particular value, no, per year, per frequency, no. So this is actually a good graph, no. And the title is actually very self-explanatory, answering what, where, and when. Okay, so another way of presenting it is, I mentioned you can actually present it with more broken lines, no. So the broken lines would actually represent that this is actually a not so important data. However, this is just to show comparison. Okay, and then we also have bar graphs consisting of vertical and horizontal bars of equal widths. And the length of the bar actually represents the frequency or the magnitude of the quantities being compared. So this is most appropriate for comparing data taken at a particular time, and may be drawn horizontally or vertically depending on available space. So this is an example of a bar graph. Okay, so the horizontal and vertical and horizontal area are labeled. No, what are these measurements? And usually the vertical starts with 0, and each graph, no, each kind of figure or graph here actually, each bar actually is represents a magnitude and has a value, no. And although what's wrong here is that it doesn't have a title. Okay, no title, no. So it should have title. And then there is a source, no, wherein you have lifted this graph. Okay, so we also have pie charts. So this usually is used to compare parts within a specific, with a whole, no. And this is usually divided into several components, and the whole may be designated as 100%, representing the whole pie. Okay, so for example, so we have history of any reported mood disorders from data October 1, 2008, with a total number of participants of 2,548. So each particular portion of the pie, each color here represents a particular percentage or the number or frequency for each data. So we have blue here represented as people with no mood disorder, violet here with people with depression, bipolar, self-diagnosed and treated only. Okay, and at the end here, we place in the footnotes where do we got this table. So this is actually a good, pie chart. So this is actually a good, no, good pie graph. And then we also have pictograph. So we use actual pictures of the objects under study. So for example, okay, so the symbols may be used must be self-explanatory, and this may also show fractional values. Okay, so for example, um, we have here blood drops. So the number of blood drops here actually refers to the number of people who are type A, type B, and type AB, and each blood drop is represented by 5 people. However, what's wrong with this graph is that it doesn't have a title. No, it should have a title. Okay, and another representation, no, like this, no, it has a title. So the number of people in each category. Okay, wherein each people now, each picture now represents one person. Okay, so this is actually a good, no, good pictograph, no, with reference below the footnotes. And lastly, we have this what we call histograms. This refers to a series of columns having one class interval and the frequency or number of cases in that class as its height. And it's actually a graphical representation of a frequency distribution. Okay, so um, here, this is actually a very good histogram, no, showing the hypertension knowledge scores obtained by 233 patients. So this would actually show us the number of people, no, or number of patients with that particular knowledge scores. Okay, so we have footnotes here, we have title, and then we also have abbreviations here defined and correctly labeled na vertical o kanang horizontal nga scales. And then scatter plot is usually used to show relationship between two quantitative variables. So a very common scatter plot diagram is you see in your CBC reports, no? So scatter plot. So represented by dots here. Okay? So this is usually what you see in your CBC results, and each dots would actually represent a particular data. So for example here, no? So this is represented by lymphocytes, monocytes, neutrophils, and RBCs, and the like. Okay? So that actually ends my lecture. Thank you very much for your kind attention. If you have questions, you can email me at briandenny@cim.edu.ph. So might as well collate your question by class because I will be posting the answers within this week. Okay? So let me end this lecture with this quote. So when you feel like quitting, think about why you started. So you've actually come really far, no? You're second year students now, and the journey might not be easy. It will actually be difficult. I will not sugarcoat things here. So, but rest if you must, but do not quit. Okay? Thank you very much. Please study for your examinations. God bless.